Hi everyone, welcome back to the Space Koala channel. My name is Luta and today I'm here with a video that has been very requested ever since my original video back in September on the Seestar Mosaic mode. At the time that was still in beta testing, but now it has been out for a few months, so many of you have gotten to try it out. And back in September, I mentioned two very important things. One was that you needed much more integration time for the signal to noise ratio. And the second one was that you would get a better result by stacking your own images. Now, ever since then, I've been getting questions, but how do you stack your own images? It is really not simple. You can't just throw them into PixInsight or whatever software you use because it just doesn't seem to work. So today I'll cover all of this. I'll start by explaining why exactly you should be doing this and why you will achieve a much better result. And then we'll get on my computer and I'll just walk you through the whole process step by step. Let's get into it. If you're wondering why you should spend time and energy stacking your own images when you get a perfectly fine stack out of the Seestar, there are multiple reasons for it, but there are two main reasons. One of them is the efficiency or lack thereof of the mosaic mode when done in the way that the Seestar does it. For the images that I will show today in this tutorial, I have used the S50, but actually the process is exactly the same in the S30. So the way it does the mosaic mode is not like a regular telescope where you would cover the first half of the image and then you would cover the second half of the image, but it just covers a tiny part of the image first, and then it just kind of spirals around. Any given time, you are only collecting data for a small portion of your image. And therefore, you have two limiting factors here. First is that you spend just a fraction of the time imaging a specific part of the image. And the second being that in between those frames, you have to spend time moving the telescope and realigning it, make sure that it is ending up at the exact place where it should. And this is why you should plan more hours for doing a mosaic image versus a regular image, because you have the same size of telescope and sensor to cover a larger area of the sky. So by definition, you will need longer for that. Now, that means that realistically, for a mosaic, you want to do it over multiple days. And then if you want to combine multiple days into a single image, the only way currently to do this is to take all the raw images and stack them on the computer yourself. Today, there is no native way to just continue stacking over multiple nights. I wouldn't be surprised if they implemented that, but currently it's not an option. The second thing that we should keep in mind, in addition to efficiency, is the very nature of stacking versus live stacking. And this has nothing to do with the fact that this is a smart telescope or that you're doing a mosaic, because it's exactly the same with a regular telescope, also if you're not doing a mosaic. And I think the simplest way to think about it is if you just imagine what the telescope is doing while you start imaging a specific area of the sky, and you start taking image after image after image. And if you focus on one specific pixel, let's say that in the first image it has a value of 200, in the second one 230, then 180, then 205, and so on and so on. So it has like an average value of 200. And then let's say that on image number 50, you have a satellite passing right over that pixel. So instead of your 200, you suddenly have a reading of 32,000. Now, a good stacking program will immediately identify this as an outlier, and that will just be rejected. It will not be used. Like, those pixels will just be discarded. The rest of the image will be used, and you move on. The problem is that with live stacking, you're very much dependent on timing, because for sure, if you get that satellite trail on image number 200, probably the Seestar will just throw away the entire image, or I don't know if it's able to do partial rejection, but even if it just throws away the entire image, that's perfectly fine. However, what happens if you get the satellite trail in the first few images? The telescope cannot see the future. It cannot know that that line is not meant to be there, because stacking is a simple mathematical operation. There's no AI involved, like selectively rejecting things. It's a good thing that it works like this, because it means that you're getting real data. But as it has no average value yet, or doesn't have a very reliable average value yet, instead of rejecting the reading of 32,000, it just builds that into the average. So you suddenly have an average that is higher, meaning the satellite trail shows up in the image. Of course, if you keep taking a lot of images over the course of the night, it will get fainter and fainter. But as long as you don't restack them from scratch, that trail will remain there no matter what you do. Now, of course, if you're doing live stacking with the Seestar and you see a satellite trail show up in the first few images, if you don't want to stack your own images, I highly recommend just like discarding it and starting from scratch, because realistically you will lose a few minutes of your time and you can get a better image if you just don't have that. But with the Mosaic, it is not really an option, because after essentially every single frame, you are moving the telescope ever so slightly to a new area of the sky. So every single frame is a first frame, that is the first one that is covering that specific area of the sky. So you will never have an existing average to work with, so you cannot do proper rejection. And therefore, the only way you can do that is by stacking all the frames on the computer afterwards. Satellite trails are a very good example because it's very, very easy to imagine and understand why it is. But this is the same for every single aspect of your image. In terms of image quality, star quality, sharpness, all of that. You cannot do any sort of rejection or weighting because you don't have all the data up front. Okay, so at this point, hopefully everybody's convinced that you should do your own stacking, and let's get into how to actually do that with the Mosaic mode. While you're shooting, there is not that much to consider, apart from the fact that if you're going to do multiple nights of shooting, you want to make sure that your frame covered is exactly the same. I think that the easiest way to do this is choose your desired framing on day one and just take a screenshot of it. You're going to take 2 screenshots. The first one will be showing the actual coordinates of the center of the image, and those will be the 2 numbers for the right ascension and the declination of where you're pointing in the sky. And then the second one will be for the rotation, and it will just tell you how many degrees you are rotated by. Having these 3 numbers, you will be able to reproduce the same exact framing night after night. So once you have all your images, let's move on to the computer. I am using an external SSD for this. This is a high-speed one that is running on Thunderbolt 4. I highly recommend doing this because it is very convenient. You don't use up space on your computer. It is very fast, and you don't have to keep writing files repeatedly on your native SSD or hard drive. I will just link the one that I use below so you can see what the properties are. So the first thing you're going to want to do is you take every single FITS file from your Seestar and you'll copy them into a folder of your liking. I called it lights. And you can see that these were taken over multiple nights from the 4th to the 6th. So that's just 2 nights. I have a total of 2,723 files. So if I multiply that by 10 and divide by 3,600, that is 7.5 hours of data over 2 nights. That kind of shows you that probably we imaged about half of the time. So once you have everything in here, the other thing you're going to want to copy from the Seestar is I created a folder called templates, and here I just have the 2 master files that I received from the 2 nights of imaging. I just compared them and I said the one that I called a ref is the one I ended up using as a reference because I just found it ever so slightly sharper. Let's start working on the images. If you have a look at the images that come out of the Seestar, the raw images, you'll notice that these are in black and white. If you know all about debayering, feel free to skip ahead, but I think it's interesting to know that this is completely normal. This is what every single raw color image looks like. That is just because the color sensor has these like mini filters, so every single picture has a different color filter in front of it. So it looks something like this. You have a red, you have 2 greens, and you have a blue. And it is a property of the sensor which order these mini filters are in, and then so you have to tell the computer this information. We have a process called debayering. And so we're just going to need to use this to give the color information back into the image. Now you see, like, pretty much the only thing that it asks you to do is to define the Debayering mosaic pattern. You can set it to auto in a lot of software. For that, it is a requirement that this information is present in the file. In the case of the Seestar, it is. If you look at the FITS header of the file and you look for a field that is called something like BayerPat, is the Bayer pattern, it is GRBG. Now, what do you do if it's not written in the file, or you don't know, or if you use a crop mode on any sensor, this information anyway gets lost. So I think that it is a very valuable skill to kind of reverse engineer this. So I'll show you how to do it. As I said, there's always two greens, and that's kind of the reason you have this almost like checkerboard pattern, because you always have the two greens that have very similar values when they're next to each other. This means that as a result of that, if you don't get the location of the two greens correct in the image, so I'll show you, you get a color image, but it doesn't look any better than it was before. And this is because the greens are not in the correct location. So actually, you don't have as many patterns as you would think, because you can have the G's in the middle, or you can have the first and the last place as a green. Now this one was GBRG. We see that we don't see that checkerboard pattern anymore. So this is one of our contenders. I will call it GBRG. Then we have the option of having the green in the first and the third place. Once again, we have a checkerboard pattern. This is definitely not looking like a real photo. And finally, we can have the green in the second and the last place. Once again, we have a weird pattern that is not random noise, but something organized. You don't want to see that. You want to see random noise. So we know that whatever we had for GBRG, so the first and the last place should be green. However, we do have two combinations because we did GBRG, but we can also do GRGB. What we're looking at is GRBG versus rotating the same thing upside down, meaning GBRG. I hope that makes sense. We can do the last option, that is this one. I will name this GRBG, and see that once again all we have is random noise. We don't have any like organized checkerboard patterns or anything like that. Each one of these looks like something that could be a real photo because we're not seeing any sort of weird patterns. We have to look at the location of the green and the red. Now let's have a look at these two stars here. We see that one of them is on the redder side and one of them is on the bluer side. I have never seen a star of this color in my life, because red stars are usually orange, and that's what we see here. So in fact, this is GRGB. It kind of makes me think that this is probably the real color. Also, we know that most of the big stars in the Pleiades are blue, and these big stars are blue, whereas here they're like yellow, red. We know that's not going to be the right color. So we can safely conclude that the correct Bayer pattern is GRBG. And if I go back to check, in fact, that's the one that was written in the file header. This is not information you necessarily need in the Seestar, but I think it's a very useful skill for anyone to have. So now that we know that this is the correct pattern, we can use that, and we will just be adding every single light that we have in the lights folder. So in my case, that is the 2723. We will add back noise and signal evaluation, and what I recommend here is that you output the files into a different folder. So I have a folder here. You can create a folder called Debayering, and you can just select that. You click on the circle to start the process, and it might take quite a bit, so go get a coffee while this is running. Okay, when the debayering has finished, you will see that we have files that are much larger, because we used to have files of 4.2 megabytes, and now we have files that are almost 25 megabytes. That is because we have added back this extra information into the image, and now the image consists of 3 channels, one for green, one for red, one for blue, instead of just the one monochromatic channel that we had before. Now our pictures look like this. And now we can get to the most interesting part of this tutorial, and that is to see how we actually register these images. Now, the main trick, I think I've also mentioned that in the original video, but I didn't go into details, is that we're going to want to use one of our original stacks as a reference. Like I said, I chose this one. So this is just going to be a template onto which we will register all of our images. So you see that these are the 4 stars. It is somewhere here, just a bit rotated. So what we want to do here is to understand where each of these frames should be moved and rotated to align with the reference image. The way to do that is to use the process star alignment. And the first thing you're going to want to do is specify the reference image. Here I will specify a file and I will select the one that I called reference. Now here, this is one of the most time-consuming parts of the process. I would recommend that you just select the slowest, most likely way that is gonna register most of your images, and just leave the computer, do something else in the meantime. In order to do that, the best way to do it is, first of all, we're going to switch from projective transformation to thin plate splines, because that is just able to apply more interesting modulations and the distortions to align your images to the reference frame. We're not going to generate drizzle data right now. We're not going to select anything else here. You're going to select all of your images from the Debayering folder here. So I have all of my images once again. We don't need to touch the format hints. We will select an output directory. I have created a folder called registered. We don't need to be touching anything else in this section. Now, these next 2 sections are the ones where I like to max out all the settings to be allowing for the most expensive computation, just because then I don't need to be sitting next to the computer and trying all over and over again. I will just know that it will take a while. To do that, I will allow any size of a star. I will say, okay, we have like 1 pixel worth of noise. We don't need to be touching the minimum structure size. We're not touching any of this. Sensitivity, I will put this up all the way. The peak response is something about how nice your stars are. It is not something I would touch. The brightness threshold, this is really how good of a signal the noise ratio do you want to have on your stars. Now here on this image, this would not be an issue, but if you have an area of the sky where you don't have any like brighter stars and your image is only 10 seconds long, you might want to bring this down to 2 or 1.5 even. In terms of distortion, if you don't mind, you can also put this up all the way. We will be allowing clustered sources because we do have only a tiny sensor, so we want to allow everything. We will always be computing the PSF fits. This is essentially a better way to understand where the center of the star is. It takes a bit longer for the computer, but we don't mind because we know that this is a difficult task to do. We will not be applying inverted image. We don't have to touch the maximum stars. Pentagons are fine for the descriptor type. Descriptors per star. The higher the value you have here, really the longer it will take for it to do anything. The maximum value is 256. And if you're not in a hurry, I would honestly do that for the Seestar images. I don't necessarily do this for my regular astrophotography career. Now, this is the next one that is going to help you a lot with registering, and that is computing intersections. Here it says mosaic modes only. However, we're not using mosaic mode here, so we're just going to select always. And what this will do is it will understand which part of the 2 images is overlapping between the image that we're registering and the reference frame. And while this takes a few seconds to calculate, it will make the whole rest of the process so easy because it will automatically know which are the likely stars to be matched with one another. And then restrict to previews. It doesn't matter, we don't have any previews. You can also enable the use of brightness relations and scale differences. You can also put that up a bit. If you do all of these settings, I can guarantee that 95% of your images will be registered on the first go. You don't have to touch interpolation, you don't have to touch anything else. You just click on the circle and then you go have dinner because it takes a while. Okay, I have all of my images registered. So these are the ones in the registered folder. I have 2,723. And you may notice that these files are even larger before. Before we were at 25 megabytes and now we're at 4 times as much. How is that possible? Well, that is because these are now registered against this image. Meaning if I have a look at what this image contains, this is the original frame that we had. And this is the part of the image that this is covering. This is now perfectly aligned, but in return, we have all this empty part of the image that just makes it that much larger. And this is why it's just occupying that much more space. This is exactly what we wanted. At this stage, we are ready to stack the images. So what you're gonna do is open the process image integration. You add all of your registered images. Once again, we are all the way up to 2723. And then here we're going to have a look at the settings. Format hints, as usual, we don't have to touch anything. Image integration. So we're going to do an average, of course. Normalization should be additive. You should never use local normalization. Of course, you can't at this point because we don't have any local normalization files. But if you were to do like a more automated approach like WBPP, it is tempting to leave that selected, but it is important to understand that you cannot do local normalization because we don't have any reference for the local normalization, because the way that should work is it should weight parts of each of these images and understand how good that part of the image is. Now, for us, each of our images only covers one part of the whole frame, so it makes sense that we can't do that. We'll leave that on the default additive with scaling. In terms of weights, you could do weighting. I recommend that you don't. And that is because the weighting is done on the whole image and not just on the individual parts, pixels that we're looking at. So what you risk is if your data is not all reliable, then maybe you had 2 hours of like amazingly clear skies where you were shooting one part of your mosaic, and then those frames will be weighted higher than the rest of the night when you were shooting a different part of your image. So you end up making your image even worse by weighting the low signal to noise ratios lower. So I would honestly put don't care, no weighting here. I don't need to touch anything else here. Then we go into pixel rejection. We do want to reject. This was the whole discussion at the beginning. You can choose whatever you like. If you have a lot of images, I would just use either linear clipping or ESD, and then you can leave everything else on the default value. I wouldn't touch anything else. You can play around with these, but realistically, it takes so long to integrate the images that you're not gonna wanna play around too much with that. You don't need to be doing any large-scale rejection. Of course, you need the signal and noise evaluation, and you click on the circle and you go to bed. Because this will take quite a bit of time depending on how many pictures you have, and then it has to integrate each of the 3 channels separately. When that is done, you will get an image. I have already saved this with the name stack 2723 times 10 so that I remember how much data I had in here. You should just save it right away because you've invested a lot of time in the stacking, and let's see what we have. Of course, I will remove the link stretch. Let's just compare it with the reference that we had before. So we have this weird like gradient in the middle, this black, I don't really know where it comes from, but it's there on both images. Now, of course, we have much better signal to noise ratio because we have twice as much data. We don't have any of those hot pixels because they were rejected by the rejection process that was not possible before. And in general, I mean, of course, you would expect to see better data because this is 2 nights versus just the one. I think it is clear this is not even something that is up for discussion. And then this is not like a processing video, so you just process it the way you see fit. Find a way to get rid of this gradient that is there on my picture for some reason and end up with a processed image. I have already had a go at it. This is what I was able to get out of it. Of course, it is still somewhat noisy. That is just my preference. because we are working under low light conditions. It is normal to have noise if you're shooting these areas with very little light with a small telescope. I much prefer to have noise than to have noise reduction artifacts, because those are so visible for somebody that looks at space pictures a lot. But in any case, anyone can process the images to their own liking. I think that this is a very nice image, considering that it was taken with one of these smart telescopes. I truly hope that this quick walkthrough lived up to the expectations of those of you that were asking for a tutorial for this. And I hope that you will get to try this out very soon. And hopefully this will enable you to get a better signal to noise ratio in those nice large wide field mosaics, because you'll be able to take them over multiple nights and then stack the images yourselves on the computer. If you have any questions regarding this process, leave them in the comments below. It is the full moon tonight, so it is not the best time to shoot. However, the Christmas period is coming up, so I will have some time off work, and I hope that's the case for many of you as well. If the weather allows, we will all get some time under the stars and shoot some images. Until next time, I wish you clear skies.